Okay, so now we will continue with special domain enhancement techniques. Uh, in previous lectures, we started with point operations. If you remember, we have seen what is thresholding, contrast stretching, negation, power law transformation, log transformation, inverse log. Then we have also seen intensity or grade level slicing, bit plane slicing. Okay, histogram equalization, histogram matching. Now we will see what is image subtraction, image averaging, and spatial filtering. Okay, so image subtraction can be done using this expression. So what is f of xy? F of xy is the original image. H of xy is another image. Okay, so we can just subtract and we'll get a new image that is called as a difference image. We will see the application of this. Okay, what should be the condition? Provided f and h should have a same size. Okay, so where will you use this? So generally this is used in medical imaging. Okay, this is also known as mask mode radiography. Here you can see this is a image. This is called as a mask image. Okay, and V is taken. This image is taken after injection of a contrast medium into a blood stream. So what doctors have done? They have injected a dye in this artery, okay, artery or you can say vein, and then they have subtracted this from the original image. Okay, so what they got? Only the highlighted artery they got. Okay, so why the background is dark in this image? Why the background is dark in this image? Because the subtraction, whatever is common, okay, you'll get the values near to zero. Okay, the difference is not much, that's why you got the value zero. For example, if you have this matrix, okay, suppose this is the matrix, and you have changed only one pixel here. Okay, so after the change the pixel may be this 10. Okay, now if you subtract this, what you will get? You will get what? You will get 0 0 0. Here it is 0. Here you will get what? 8, and this is 0. So only the change you will get, right? Remaining everything is 0. 0 is what? Black. That's why the background becomes black, and only the change will be highlighted. So that is called as image subtraction application. So suppose for example, the car is moving on the road, okay, and the background is stationary, and if you subtract the first image and the last image, you will get only wherever there is a change. Okay, remaining everything will be zero. So image subtraction is used for change detection. Very important application. For example, if I want to find out a change in Mumbai area since 1993 till 2020, so how will you do this manually? If you try doing this, it is going to be a very difficult task. So we can take the satellite images of since 1993 till 2020, and we can do the apply subtraction and do the analysis, and we can say that the settlement has increased by this much percentage, the forest has reduced, mangroves have reduced, and so many things we can analyze using this image subtraction. Now this image subtraction is a very basic technique I told you for change detection. The base is same, but means for higher algorithms also we are using the subtraction technique only, but there are many other ways also to find out the change. Okay, now we'll see what is image averaging. So now you know what is f of xy. F of xy is the original image. Okay. So if the noise is present in the image, okay, what we'll get? We'll get a noisy image. So f of xy plus n of xy, where n of xy is a noise, uh, it's an additive noise. Okay. So we will get the noisy images. So what we are saying is, if you take the multiple noisy images, okay, G1, G2, G3, G4, okay, multiple noisy images like this, and if you take the average of these images, okay, whatever the result is, here it is shown by G bar, that will approach the original image. Okay, I repeat again, here in this formula you will replace this GI to G, G1, G1 plus G2 plus G3, it will be like this, right? G1 plus G2 plus till G of Gm, okay? Divide by n. So as you increase m, that is total number of noisy images, this G bar will approach original image F, which is a noiseless image, right? It's an original image. So generally we use this in the field of astronomy. Here you can see the first image is the original image, which is not a noisy image. Okay, we are expecting this image, but suppose we got this image which is a very noisy image. You can see that, right? Noise is present. Okay, so what they have done is they have taken 8 versions and average of it. Similarly here 16, then 64 and 128. So this is m, right? We are increasing the value of m. Now visibly also you can see that this image, original image and this image, okay, it is much closer to each other, like similar to each other compared to remaining. Okay, so what we have done here, this is a difference of 1 and 3. Okay, then this is a difference of 1 and 3. This is 1 and this 4, then 1 and 5, and 1 and 4 5 6. Yeah, 6. Okay, so what can you say about this? See, one, the difference is what? Minimum here. That's why this image is dark. Why? Because see the histogram is on left hand side, so you know that this is a dark side and this is a bright side. Okay, since the difference is less, okay, the values are near to 0, so this image is near to original image, noise free image. Okay, now we'll see what is neighborhood operations. I mentioned this before also. There are two types of operations basically in spatial domain: point operation and neighborhood operations. So point operations already we have seen, and that time I told you that what we are doing in point operation, we are taking one particular pixel, applying a transformation on this, okay, and we are getting a new gray level value and writing into a matrix at the same position, respective position represented by the S. So this is what point operation, right? Now we'll see what is neighborhood operation. So while learning connectivity of pixels, what we said is that each and every pixel has how many neighbors? 8 neighbors. So now in this neighborhood operations, we are going to calculate the value of this particular pixel based on the values of the neighborhood. So we are going to consider all the 8 neighbors to find out this value. Okay, so this is not one to one. Like in this case, the value was only depend upon that particular pixel. Here the value will be dependent on the neighborhood of the pixel. Okay, so filtering is one of the neighborhood operation. So what is filtering, that we'll see in detail now. Okay, so use of special mask for image processing. So filters are also known, filtering is also known as masking, and why we do that, that we'll see. There are two types of filters: linear and non-linear filters. In DSP you must have studied low pass filter, high pass filter and band pass filter. Okay, so you know that low pass filter eliminates or attenuates high frequency components in frequency domain and result in image blurring. Okay, high pass filter attenuates or eliminates low frequency components. Okay, it results in sharpening edges. How it is resulting in the sharpening and blurring, that I will teach you. Okay, and band pass filters removes selected frequency regions between low and high frequencies. Okay, for image restoration. This is not used for the enhancement techniques, that we will see later on. So now you must be wondering that we are talking about spatial domain. We are not talking about the frequency domain. Then what is frequency in an image? Okay, so I will explain you that first. When, if this is the image, okay, if this is the image, and um, this is suppose black, this is white, and this is black. Okay, so if I take one scan line from A to B, A dash to B dash, okay, how will you plot the gray level profile of this for A dash 2b dash. So this is 0, right, because this is black, then white, okay, then black. This is correct. Now instead of this, if I have these bands, okay, now see, this is black, this is white, this is black, this is white, this is black, this is white. So what will be the gray level profile here? Black, then white, black, then white, black, then white. So what is happening? Okay, now you can see when you scan the image from left to right, the frequency is what? It's a variation in gray level, right? If the variation is more, the frequency is more. If the variation is less, the frequency is less. So suppose this is the image having constant gray level value. So this is white. So all the pixels are having value equal to 255. So what will be the frequency? Frequency will be 0. Why? Because there is no variation in the image. It has a constant value. Okay. So the frequency is 0. Instead of that, if you have this pattern, what can you say? You can say that the frequency is there, right? The frequency in vertical direction as well as in horizontal direction, right? Because the variation is there in this direction also and in this direction also with respect to x and y. Okay, so this is called as a frequency in spatial domain. Okay, so variation in gray level values when you scan the image from left to right, top to bottom, that is called as a frequency in image. Very important concept. Otherwise, you will not understand how the filters work. Okay. So, what we do here is we are taking in DSP you must have applied one dimensional signal on another function, right? Y of x on f of x may be, okay, using which operation? If you remember, convolution. Okay, convolution. So here we are talking about two-dimensional function. Okay, so if your image has two dimensions, your filter will also have two dimensions. Okay, so filter mask, that is that function, filter function is called as filter mask or template or kernel. Okay, so what we are going to do is we are going to put this mask on the image and then apply some calculation, maybe a convolution operation, and then find out a value for that particular pixel. So that is what is shown here. Okay, so okay, well, this is the filter from filter mask. Mask which is shown here. Okay, and the values in the mask. Okay, the values in the mask are known as filter coefficients. Okay, we are not calling that as a pixel, but in the values in the image is known as what? Gray level value for that particular pixel. Okay, so here we have shown 0 comma 0 here, minus 1 here, plus 1 here. Okay, do you remember this? 0 1 and this is 0 minus 1. Okay, why? Because this is your 0 0. This I have taught you in the first or second lecture. Okay, and your image will have same coordinate value. This is what? X comma y. This is x minus 1, y minus 1. This is x plus 1, y plus 1, and so on. Okay, so in convolution operation, what we do is we are going to place this mask, this 3 by 3 mask on this 3 by 3 image. Okay, so after placing this mask on this image, we have to multiply this value with this value. Okay, so w minus 1 minus 1, w minus 1 minus 1 into f of x minus 1, y minus 1 plus w minus 1 0 and f of x minus 1 y. Okay, plus this is what? W00, it's a center element, into f of xy. Okay, so on. So what you will do? You will do this for all 9 elements, and whatever value you will get, okay, after doing whatever value you will get, you are going to write at the center. Okay, so to find out the center element, you are going to apply the convolution. Okay, So if this is the mass, this is the image. Okay, I'll show you. This is the image. So I'm writing this values as suppose Z1, Z2, Z3, Z4, Z5, Z6, Z7, Z8 and Z9. Okay, and this is my filter function having coefficients W1, W2, W3, W4, W5, W6, W7, W8, W9. Now if you remember, okay, if you remember in DSP you said that for convolution operation you have to reflect or flip or rotate the function and then apply. Okay, here we don't have to do that because the filter function is mass is symmetric, so even if you rotate you will get the same values. Okay, so what I'm going to do is I'm going to put this mass on this image such a way that the center of the mass, okay, is aligned with the center of the image. Okay, so now what is there on top of Z1? W1, this is W2, this is W3, W4, W5, W6, W7, W8 and W9. So this is what is written here. Okay, the value at the center, the new value at the center of the new image. Okay, new image will be also having size 3 by 3 and we are trying to calculate this value. Okay, so the new value R will be W1 Z1 plus W2 Z2 plus W3 Z3 till W9 Z9. This is what is shown here, and this and this is same. Okay, here I have written in terms of x and y coordinates. Here I have directly wrote this so that it's very easy to understand. Now here we have taken 3 by 3 filter mask. Okay, you can take 5 cross 5, 7 cross 7, 9 cross 9, 11 cross 11 and so on. Odd size mask only we take because the center of the pixel, center of the filter function should align with the center of the image matrix. Okay. Okay, so now this is a generalized formula for the convolution that you have to remember. In practical you can use the same thing. If you open this, okay, if you open this you will get the same formula. And what is this? Minus a minus t minus a plus a, this is the mask size. Okay, so if I have 3 cross 3, this s will vary from -1 to 1, right? -1 0 1, and b will also vary from -1 to 1. If it is 5 cross 5 means it will vary from -2 to +2. So it will be -2, -1, 0, then 1 and 2. Okay, and so on. So when you write the code in MATLAB or any programming language, you will have 4 for loops. Okay, one is for x, y, s and t. So there will be 4 for loops and then you are going to write this formula. Okay, now suppose your image is like this. Okay, maybe n cross n, and you are using 3 cross 3 image matrix. Okay, so let me draw this 1, 2, 3. So what I am going to do is I am going to put this mask on this image. Okay, so now what will happen? I'll get this as a first value, right? So what will be the resultant image? In that case, the resultant image, the first value will be this value, right? So what will happen? The size of the resultant image will decrease. The size of the resultant image will decrease by 2 rows, 2 rows and 2 columns. Okay, so this is the first, this is one of the method of applying convolution. If you apply that way, then your image output image size will decrease. Okay, another method is if you want to start with this particular pixel, okay, if I want to consider this particular pixel, I have to put the mask like this, right? I have to put the mask like this. So what I'll do is I will pad this entire image with zeros. Okay, I will add this data, dummy data. So now I can place the mask like this. I'll get the same size here. The problem with this is because this is 0, at output you will get a black border. That is the problem. So this is the second method, but generally we use this padding, we use this method. Okay, and the third method is, instead of adding 0, you can repeat the first row, first column and second row, sorry, first row, last row, and first column and last column again. Instead of zeros, you will repeat the values here as it is and then apply the mask. So these are the three common methods generally used while doing the convolution. What is the first method? First method, either you start from second row, second column, the first pixel. So, but what is the disadvantage of this? The size of the image, output image, will be smaller than the original size. Second method, what I told you, pad the image with zeros. Okay, what will be the problem? The border will be visible, it will be a black border. And third is what? You can replicate these values. First row, last row, first column and last column, and then apply convolution. This is what is explained here. Okay. Padding with 0. Okay. Now we'll see low pass filter. Okay, low pass filter is also known as smoothing or blurring filters. Okay, generally used for blurring, to remove the small details. Okay, and noise. These are the main advantages of applying low pass filter. Okay, so low pass filter, here we are going to see the averaging filter. Okay, why it is known as averaging filter, that I will tell you. So this is a mask commonly used for smoothing filters or averaging filters. Okay, so this is a 3 by 3 mask, and the property of the averaging filter mask is the sum of all the coefficients of the mask should be 1. Okay, this you have to remember. Okay, if I add all these things, I'll get 1. If it is 5 by 5 image, if it's a 5 by 5 filter, okay, if the filter mask size is 5 by 5, the element will be what? There will be 5 rows, 5 columns here. Okay, and this will be 1 by 25, because sum of all the coefficients should be 1. So you can generate your own mask and apply it. So this is a basic mask commonly used. Okay, and here this is also a low pass filter mask, but this is called this is a weighted averaging. So at the center, um, four more weightage is given, then this 2 2 2. Now here also, if you check, the sum of all the coefficients is equal to 1. Okay, so we will apply these filters on the image matrix while solving the problem, and you will come to know the difference. So here you can see this is the original image, and original image is given, and this is averaging mask. These are the filters, which are different filters used: 3 by 3, then 5 by 5, 9 by 9, 15 by 15. They have increased the size of the mask, and you can see the blurring is more. So as you increase the size of the mask, as the size of the mask increases, blurring will increase. Okay, blurring will increase. It's just like a order of filter. And why? See here, this is visible, the padding, black border is visible because of the padding. Okay, so why it is why the blurring, how it is happening, blurring? Okay, what is happening is, when you apply a mask, suppose these are the values, 4, maybe 2, and then 1, and 3, 5, 1, 4, 2, 2. Okay. So if I apply a low pass filter mask, what is the mask? What is the mask here? 1 by 9, 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 1 by 9. Okay, ideal. Just now we have seen that mask. So what is happening? This into this. Okay. So what is the value here? What will be the value at the center? Okay. So 4. Can I write 4 plus 2 plus 1 plus 1 plus 3 plus 5 plus 4 plus 2 plus 2 divided by 9. So what we are doing? We are taking the average only. So that's why it is called as averaging filter. Okay. So when you apply an ideal low pass filter, okay, we are actually taking the average of all the values and writing here. Okay. We are taking average of all the values and writing at the center in the new matrix. Okay. So that's why it is called as averaging filter. One more example here. This original image is processed. See, there is some noise here, unwanted pixels, bright pixels, which we are not interested in. So we have applied the image mask of size 15 by 15. So this is blurred image, but I want a clear image, and also I want binary image. So I will apply thresholding and I'll get this. Okay. Okay. Now next is median filtering, also known as order statistic filters. These are non-linear filters. Okay. Averaging filter is a linear filter. Median filter is non-linear filter. So the basic application, okay, of median filter is also removing noise. Okay. Averaging filter also removes noise. Okay, but it removes the Gaussian noise. Okay, and one more example, one more application. Suppose in fashion photography, okay, if you want to remove the wrinkles on the face, we can use smoothing filters so that the wrinkles are gone. Okay, and we feel that the skin complexion is very good because of that. Okay, so median filtering, you know what is median, mode, you must have studied in mathematics. Okay, so the median here is same as what you studied in mathematics. So generally this is used for the impulse or random noise. So what is impulse noise? It's a sudden spike. Okay, that is called as impulse noise. So the sudden noise is used to reduce the sudden noise. We use median filter. Why? That we'll see. Okay. So the gray level of each pixel is replaced by the median of the gray levels in the neighborhood of the pixel. So here we are not going to take the average, but what we are going to do is whatever neighborhood values are there. Okay. First thing, we are going to sort it from lower to highest. Okay. Lower to highest. So suppose this is 10, 15, 20, maybe this is 0, then you have 255 here, then 11, 10, 9 and 7. Okay, so I want to replace this value. Why this value? Because in real life you will not get this type of image, okay, having sudden change in for only one pixel. Okay, there is sudden change for one pixel, so this we can consider as a noise. Okay, white bright pixel. Okay, so if I want to remove this, what I'll do, there are how many values? 9 values. So I will arrange it from lowest to highest. 0, then you have 7, 9, 10, 10, 15, 20 to 55, right? 1, 2, 3, 4, 5, 6, 7, 8. I have missed one. 10, 10, 15, okay, 11. So somewhere here, this is 11 and this is 15. Okay. So what is the median? 1, 2, 3, 4, 5. This is the median, right? So in the output matrix, we are going to write this as 10, 15, 20, 0, and we'll replace 255 by 10, 11, 10 and 9 and 7. So we have removed this noise, right? Bright pixel. So this is called as median filter. So the original value of the pixel is considered in the computation of the median. So we are going to consider all the 9 values to find out the median value. Okay. So the advantages of median filter is it's very popular for certain types of random noise. Okay, it provides excellent noise reduction capabilities with considerably less blurring than linear smoothing filters of similar size. What is the meaning of this? Suppose this is the image. Okay, this is the image having noise in this. Okay, it has a noise. Okay, we want to remove this noise using suppose averaging filter. First filter which we have seen. So what will happen? Okay, what will happen? We are taking the neighborhood, taking the average, writing it here. Okay, we are doing it for all the windows here. Okay, so what will happen because of that? The edges here. Okay, the edges also gets blurred because we are taking the average of this. Okay, so what will happen? You will the entire image. The noise is eliminated, but along with noise, the edges are also getting blurred, and that is unwanted, that we don't want. Okay, so median filter is taking care of this. Median filter will try to preserve the edges compared to averaging filter. Okay, that is the main advantage of using median filter. Another advantage of using median filter is while doing the average, what happens if these are the values of the image. Okay, where the previous, suppose this is the value of the image, uh, image matrix. So maybe like this. So what happens, like when I want to replace this particular value by averaging, I'm going to take the average of all the pixels and writing it here, and the resultant value, okay, is not from the image itself. It will be in between. We may get the values like maybe some 20 point something, okay, which may not be a part of the original image, or may not have the value is not present in the original image. Okay, so we are introducing a new gray level value in case of averaging filter, which is not desirable. Okay, but in median filter we are going to use the value which is already present in the image, one of the values of these 9 values, and that only we are going to write here. Okay, so this type of filters are, I already mentioned, is used to eliminate impulse noise, random noise. It's also known as salt and pepper noise. So salt is what? White bright pixels, and pepper is black pixels. So on the bright background black pixels is pepper, and on dark background white pixels is called as salt. So this is the example which I have given for 3 by 3 median fifth largest value. So this is given here. You have to sort it, and you will take the median value. That is what, after sorting you will get this from lowest to highest, and 1 2 3 4 5. So this is the fifth element. This median value is 20. So we are going to replace the value by 20. Okay, here you can see the effect of median filter and averaging filter. This is the original image. After applying averaging filter, the image has become like this. It is blurred. Okay, the all the edges and everything, the information whatever is there, that is also getting affected because of the averaging filter along with the noise elimination. But if you see this median filter, okay, this is quite better outcome. Okay, so this is the difference between averaging and median filter.